Today, solving the Riemann hypothesis with Euclidean geometry. First thing you'll need to know, or to at least understand how this was done, is how to trisect an angle. Here's a short explanation. You can look on it, how to trisect it. And some examples, just to go quick. I do have a video online showing how to trisect any angle. This one's a 60 degree, the one I did online. But once you can do that, and here's a few examples. There's some variations, 46. Now rules change inside after 60. This vesica Pisces here, or this trisection where the circle goes through, on the second one, will start to extend out. As you can see, where you go from this angle. So you have, once you go past 60, you have to then do your line here. One thing I didn't reveal in the video. And also then once it goes past this one, 81, you can, or 80, you can actually use the peak of the vesica Pisces. And another way to prove a right angle is you can, when you do the same method, the circle, and once you use the circle that goes to extend, the line will always be a 90-degree angle right there. And you can go beyond 90 degrees. But once you could do that, then you can trisect other shapes, get shapes that you couldn't do just by secting angles. See, this one's 90 trisections. It's 5 split into 3, became 15, and then the 15 was divided by 3 again, giving 45, and you automatically got the bisector on that, giving you 90. There's 36. And some of this is compass and straight edge. Supposedly impossible to do, but so is solving the Riemann hypothesis. But this is how it relates to the Riemann hypothesis. This isn't the only method for trisecting it. They only come up with one method, but as in mathematics, there's usually an inverse once you figure it out. Now the second way, trisecting an angle, is kind of by a flower of life. You take a circle, draw all the circles out in this, and this is by how I'm giving the Euclidean proof, because now you have concentric circles. These give you equilateral triangles, and this will give you a 60-degree angle between here. This is automatically the bisector. You get the bisector, just follow up the split, and you can see this is given to you there. Now, one thing about this, and you can see this is the vesica Pisces. I count this 1, 2, 3. You'll see where that's relevant in a moment. Now here's the way you don't want to do it, because what we're doing is taking the flower life and doing it in between, and that's giving you the other angles. But this one does. Now I've just continued on that. Now this will give you the lines in between. And now here's the first, second, third, and you can see how each one is giving you that many divisions. Now, before, if you use the method, this line here, the problem is you can always trisect the triangle and get these ones right, or if you were going to this intersection right here, in between, or on the third, it would be right here, excuse me. Now here's the difference. Here's the arc of the circle at 3, and any point there, if you want to trisect 60 degrees, this one actually, you can see if I extended a line, that would be off, but let's see, go through that same bisector. Now that would be off right there. It doesn't give me the angle. But now if I extend this perpendicular through this vesica Pisces straight up through the arc, that is actually gives me a trisection of 20 degrees, and you can check that with a protractor. But any of these things I'm showing you, you can duplicate yourself with a compass and straight edge, not using anything. Because the one I'm calling 1 is just the theoretic radius of the circle. That's it. It's just a relative to the circle, in essence. Now once you can do that, you can also break that down to drawing any prime number of a circle, because this kind of demonstrates off there. But in essence, if I want to do 7, or let's skip ahead. This is just now dividing that up a little farther. It's a fractal now on each triangle. It kind of goes to Pascal theorem, but I'm setting it up on a different Hermitian matrix, or I'm setting on a Hermitian matrix in the vector here. Now, everyone, the red numbers is a prime number. And you can see as I split all I'm doing is see 6 there. Now once I get the division, because once I go up, it's automatically giving me the pink is in 12 divisions on that. So it's fractaling down and converging. Now I can do it forever, theoretically, because like the Zeno's paradox, you'll never get to 0. But here's where it comes down to prime numbers, because now you can see where the prime numbers come with the Riemann hypothesis is how can you find all the prime numbers? Now there's the solder sleeve, but I'm saying it wrong. But anyway, another C for prime numbering is the Riemann zeta function. Now how the Riemann zeta function works is basically, if you look, I'm just having is 1 plus 1/2 plus 1/3 plus 1/4. It's just the fractions, but that's what I have. I'm just have the 2 there is give me a fraction. Now I can keep dividing that on, but the one commonality, when I keep dividing out, 7 will become 14. It still shares all the things. So in theory, when I bring it down, shrink 7 down to here, fractal into 1/2, all those lines are still on the same angles. The angles always stay the same. So this is a Euclidean proof by angles, in essence, because the Riemann hypothesis is then also that all prime numbers have real part on 1/2. Now how does a real part 1/2 on the real number line?